you are now ready to go. The problem with after lunch session is that it's too good food are providing by the organizer and staying awake is the problem, right? But I think the kind of presenter we have now, like Dr. Siparna, I think it's very exciting. So let's start the session. We have two exciting talks in this session. We have a lot of discussion in the first half. We have from system architecture to EDA, then recommendation system to database. We have learned everything almost, right? Now again, time to go back to the machine learning. And no other than Dr. Siparna, she is one of the well-known in this domain. So let me just read her biography briefly. So she is currently Associate Professor in the Department of Computer Science and Engineering, IIT Patna. Her research interests include natural language processing, generative AI, multi-objective optimization, and biomedical information extraction. She regularly published in all reputed venues. I know very well that. She is the recipient of the Fulbright Nehru Academic and Professional Excellence Fellowship 2025, Humboldt Research Fellowship, Google India Women in Engineering Award in 2008, INSA Young Associate 2024, INSA Distinguished Lecture Fellow 2025, Nasi Young Scientist Platinum Jubilee Award 2016, ACRB Women in Excellence Award 2018, Pattern Recognition Letter Associate Editor Award 2023. She received several Best Award awards. So what you?
Thank you. I hope I am audible. No? Okay. So very good afternoon to all of you. So this talk is not on exactly on machine learning, rather on natural language processing and how we are applying the generative AI for solving some problems of natural language processing. So in this talk I will mostly discuss about some of the challenges in the healthcare domain. As a case study we will discuss the healthcare domain, and I will showcase you how we are using the NLP and the generative AI tools and techniques for solving the problems of the healthcare domain. So that's why I have given the name the harnessing the generative intelligence for healthcare. And we are also building some small language models in IIT Patna in association with some companies for the animal sciences. So I will also showcase you the steps that we have taken for building the small language model and also some benchmark data sets that we are developing. Yeah, so you know that multimodality is nowadays a very common term, or the very popular term that we are using in our day-to-day activities. And multimodality is somehow mimicking our real life experience. Like in our real life also, whenever there is an object and we have to take the decision about an object, we are utilizing our multiple sensors. Like we used to see the object, touch the object, feel the smell of the object. By collecting the information from multiple sensors, we used to take a decision about the object. So similarly, there are many tasks in the natural language processing where you need to collect information not only from text but also from images and also from the videos. And social media platform is an example of multimodal data when we are not only uploading the textual information but also some images and also videos. So that way everything is becoming multimodal nowadays. And another important thing is that image and text are somehow complementary to each other because some information, there are some abstract concepts like love, affection, freedom. These concepts you can better describe using text. But how a piano looks like, you will not be able to describe using text well. Maybe you need to take the help of an image to better describe the concept. So image and text are also complementary to each other. So this is basically another advantage of multimodality. So there are many tasks in natural language processing. For example, in the left hand side I have shown you the task of emotion recognition. So when you have to identify the emotional state of a particular speaker, suppose two speakers are discussing on a particular topic, maybe regarding a movie or some sports event, and you need to detect the emotional state of a particular speaker. Initial days in the NLP, in the traditional NLP, we used to see the utterances, what the speaker is saying. But now we are also seeing the facial expressions or the audio tone. If the speaker is sad, then the audio tone will be low, and if the speaker is angry, then the audio will be high. So the pitch, tone, facial expressions all together help us in understanding the emotional state of the speaker. Similarly, in the right hand side, I have shown you the examples of multimodal summarization. So when there is a disaster situation has happened, people are posting about the disaster in the social media. So suppose there is a flooding situation and the physical connectivity is lost. The people are simply connected in the social media. So they are reporting about the current situation in the social media. So you can download all the social media posts, and then you can filter out which are relevant, which are not related. And then all the informative posts can be summarized, and the summary can be given to the rescue team, and the rescue team can plan for the rescue operation. So this is again an example of multimodal summarization. Similarly, in the healthcare domain also multimodality is becoming very, very popular, especially in the patient care, like whenever suppose you have to take a decision about the patient, like for example cancer patient. So for the cancer patient, we do not have the image data, rather we also have some gene expression data or some some reports, genetic reports, or the biological data, some clinical reports. So it is becoming multimodal nowadays. So we have multiple different sources of information, and by considering this genetic information, DNA information, image information, we have to predict whether the patient will survive for more than 5 years or less than 5 years. Similarly, when suppose you are giving a therapy to a, like by counseling advice to a mental health patient. Suppose a patient is suffering from some mental disorders, and the doctor has to predict, or suppose there is a AI bot, and the AI bot has to predict what kind of disorder the patient is suffering from. The disorder can be anxiety, bipolar disorder, or depression, and there only the utterances are not enough. The patient's audio tone, the facial expressions, these are also giving us enough clue in understanding the mental disorder of the patient. So this way in healthcare domain also, there are many applications of multimodal information processing. So motivated by this, but there are many challenges also. Like when I am talking about the multimodality, obviously collection of data is very, very important. Like for each patient, just think about, like in the cancer case, if suppose there are 3 modalities like DNA profiling, genetic information, and the image data. So if suppose you have fixed that you will be using these 3 modalities, then for each patient you need to have these 3 modalities. So how difficult it would be for the doctors to collect the information for each patient for these 3 modalities. So often you need to handle the missing modality. So for each patient you may not get all the 3 modalities. So your algorithm should be robust enough to handle the missing modality. So maybe for one patient the DNA profiling will be missing. For the other patient, genetic information will be missing. For the third patient, maybe the captured image will not be good. Okay, so how your model is capable of handling the missing modality situation? Okay, so then when we are designing the algorithms for the healthcare domain, interpretability is another important factor. No, we are like for the other like I have shown you the disaster management, or maybe the emotion detection in the other domains, in the sports domain or in the movie domain. So there maybe people are not more concerned about the interpretability. You just simply give the emotion state and maybe that is sufficient. But here doctors will not buy your algorithm unless and until you are also giving some interpretation. That why you are saying that the patient will survive for more than 5 years. What is the reason behind that? So you also give a meaningful interpretation behind the outcome. So and also ethics and bias. So like all these algorithms, like whatever algorithms we are nowadays using in the healthcare domain, they have their own biasness. So how to overcome this kind of biasness? So these are several challenges when we are applying the models in the healthcare domain. So So, our team in IIT Patna, we are having a team called AI NLP ML, and we are using this multimodal data for solving several tasks in natural language processing. So, for example, we are solving the task of dialogue systems, like developing some chatbot, and this chatbot can be a healthcare chatbot. Like one of my students has started his own startup in the clinical AI assistant. So this is a chatbot which is helping the doctors in symptom investigations. In a healthcare setup, in a big hospitals, doctors are already overloaded. Like initially the patient is visiting the hospital with some self-report, like I am suffering from fever and cough for last 5 days. So that way the patient is going to the receptionist. The receptionist used to send the patient to a particular department. Now in the department there are some junior doctors and there are some senior doctors. So these junior doctors used to do the symptom investigations. So can we have a bot there, chatbot there, which will do the symptom investigations? And this bot will prepare a report, and this report will be verified by the senior doctor, and finally the senior doctor will prescribe the medicine. So my student has developed his own clinical AI chatbot, and obviously in the background there is a knowledge graph, and this bot is understanding the symptom and image associations from the knowledge graph, and then asking the relevant questions to the patient. So bot cannot ask the unnecessary questions, cannot repeat the question, so there are several constants. Okay, and it is obviously based on the reinforcement learning concept. So then we also work on the complaint mining. So complaint, nowadays we are purchasing many products online, and then we are not happy with the products. So we want to write the complaint in the online platforms. And these companies like Amazon, Flipkart, all these companies receive complaints, so many complaints in a day, and also so many reviews. All the reviews are not of complaining type. So they want to basically separate which are complaining type and which are normal reviews. And they also want to go into detail, like a product can have many aspects. For example, a mobile phone has a battery life, camera quality, screen size, color, or the price. So these are the different aspects of mobile phone. So the person may be complaining about the battery life but happy with the price. So on which aspect the person is complaining about, this is called the aspect based complaint mining. So here also it is multimodal, because when you are writing the complaint, person is also uploading the image and also a small text he or she is writing. So we are also working on multimodal aspect based complaint mining, and several other tasks like understanding the bullying, like given a meme, and memes are collection of text and image. So whether if the meme is written in code mix language, so being multilingual, Indians often switch between the languages. So can we understand the meaning of a meme? And memes are often sarcastic also. So you need to again understand the meaning of the image and also the meaning of the text in sync, and then only you will be able to understand whether the meme is offensive or not. So again, it is a multimodal information processing task. So there are several application areas where we are applying this kind of multimodal information, multimodal data. So moving forward, so in my talk I will showcase you some of the tasks in healthcare data where we are successfully applying the multimodal information processing, and how we are modifying the fusion architecture in solving so, because ultimately when you have text and image data, somehow you have to fuse them. Okay, so in some of the some of our application areas, we are also modifying the attention mechanisms. Okay, because attention is the very basic mechanism by which the given a text you can put like given an image, maybe the entire text is not important, so you can put focus on only few words on the text. Okay, so this is called the attention, and this was the paper which came up in 2017 attention that is all you need. And there are some researchers by Google, they proposed this idea that after the invention of attention, it was quite easy in the NLP research to work on to understand the long sentences. Like even if you have a long sentence, understanding the meaning of a sentence became very easy. So how we are modifying the architecture of this attention, that I will showcase you in some of our work. So this is the work that we have done in IIIS 2024. That here basically we solve the task of multimodal medical question summarization. So the task is that when nowadays whenever we are suffering from some medical disorder, we report to a doctor or we go to a doctor, but in order to take the second opinion, this is very popular in Western countries. There are many medical blogs and medical forums where you can also write about your problem. Okay, you can mention about your disorder type or you can mention about your problem. And there are many other users who are associated with these medical blogs and medical forums, and some doctors are also associated with these medical blogs and medical forums. And you know that these doctors can give you some solution. So these are called the medical questions. So you are writing your problem in natural language, and maybe you are describing your problem very long, like you are writing unnecessary stuff also, which are not necessary. So doctors do not have time to go through such a long text. Okay, so they need a summary of the question so that they can quickly go through the question and they can give a solution for the same. So this is called the medical question summarization. But we made this multimodal. So what we understand is that there are some symptoms. So for example, we identified these few symptoms. You can see like lip swelling, swollen tonsil, mouth ulcer. Like we categorized with four categories: ENT, eye, limb, and skin. And we identified that these external symptoms can be easily expressed by some images. Okay, so when people are writing about their disorder type, they can also upload an image and they can refer to the image and they can describe the problem. So this way the problem will become multimodal, the question will become multimodal. So it will give a ease to the user also, because now you can always refer to the image and you can describe your problem. So we made the dataset multimodal. So this was our first contribution. So before that, nobody has done any work on multimodal medical question summarization. So this was the first study on multimodal medical question summarization. So there was a healthcare magic dataset where there are 3015 question answer pairs, clinical question summarization pairs, but no images were associated with the dataset. So we made the dataset multimodal. So there are four categories in the dataset: ENT, eye, limb, and skin. And you can see these are the different symptoms. Like under ENT we have the lip swelling, mouth ulcer, swollen tonsil. Under eye we have the swollen eye inflammation, leachy eyelid, eye redness, limb edema, hand pumps, foot swelling, neck swelling, knee swelling, skin rash, dry scalp, skin irritation. These are the various symptoms. Which basically this work is done in collaboration with a doctor, and he basically mentioned that these are the possible symptoms where images are possible. So we made the dataset multimodal, and then it was dataset is one contribution. Another is that time only the generative AI models, the ChatGPT and all the LLMs became very popular, because we started the work in 2023, and we want to see whether inferences is sufficient. Okay, if you do not want to train any model, we simply want to do inference of the existing models. Can we solve the task without any training, any new model? So this is simply a pipeline based approach. So we initially given the image to a blip, so the clip model. So the clip model is a visual VLM. So we ask clip, you identify the medical disorder which is mentioned in the image. So clip is giving us three possible medical disorders which are mentioned in the image. Then there is a LLM. We ask this LLM that, see, this is your question and these are the 3 possible disorders. Can you now identify which is the most probable disorder? Then there is a LLM which is generating some context for the question. So given the disorder, we are extracting some additional information about the disorder. We are asking some additional question like, what are the symptoms for the medical condition, discuss it in a short paragraph, what tests and procedures to be done for the given medical condition. So this way we are extracting some additional context. And then in the third step, maybe in the previous step there are some additional context. So we are checking the similarity between the context and the image, and if some sentences are not relevant, we have discarded them. Finally, the context and the question are given to the LLM, and we ask LLM to generate the summary. Okay? And then, so this is completely a pipeline approach. There is no training involved in any phase. And we varied the LLM in different stages, and we did an application study also. That why LLMs are, like why all these modules are necessary. So these are some of the results you can see, like when we are using the GPT 3.5, because that time these LLMs were only popular. That's why we have used these LLMs only. So when GPT 3.5 was used, so we are getting around 40% Russell score. So Russell is basically a metric which is used to compare the generated summary. Like it is a string matching. So you know the original summary, and now you can compare the strings, some consecutive words. How many consecutive words are matching with the generated summary and the actual summary. So that is the Russell score. And we have also done some human evaluation. So human evaluation means, as this is the healthcare sector, so you know that generated summary should be checked by the doctors. So we randomly selected the 100 summaries, and we asked the doctor to basically manually evaluate the summaries. So based on some parameters, like you know that originally maybe some symptoms were present in the original summary, original question, and how many symptoms are preserved in the generated summary. So if suppose in the generated summary we are some symptoms are missing, then the score will be less. So this way we evaluated the summary manually also, and the manual evaluation is also giving that the model is doing best in terms of the other applications. Now moving forward, what we have done is that, you know, the previous work was in English. So we also wanted to test whether the model is also working fine in the code mix setup. As I mentioned that Indians generally speak in, or whenever they are writing in the social media, they used to write in code mix language. So code mix means the code switching, like the switches between the languages. Like we often know multiple languages. So whenever we are writing in the blogs or in the social media, we often switches between the languages. Okay, so we wanted to test whether the previous architecture is also sufficient for the code mix language or not. Okay, so what we did first, we translated the data, which in the previous data is having 3015 question summary pairs. So we translated the data into code mixed question summary. Summary is still written in English, because the idea is that the summary will be checked by the doctors, but the questions are translated into code mix language. Okay, so our code mix ratio is 30.5. So all the medical terminologies are kept into English, and the other words are translated into Hindi based on the context. All the other medical terminologies are mostly kept into English. That is the instruction we have given to GPT 3.5, and with the help of GPT 3.5 we translated the data, and then we verified by the doctors that whether the translation quality is good or bad. Somehow the previous pipeline architecture was not working here. Okay, it was not able to handle the code mix data. So we basically fine-tune the LLM by using QLoRa. So that's why there was a necessity of fine-tuning. the LLM by using QLoad adapter. So we inserted an adapter and we fine tune the QLoad adapter by using this new data, which is having 3015 instances. So we taken the embeddings from the image, embeddings from the text, and then we concatenated them, and then we have basically fine tuned the adapter. And you can see that we are able to get around 38% user score by using this Llama 2 model. So moving forward, so here we are solving the summarization task. So you know that summarization is a very important task, as I already mentioned during the disaster summarization. So suppose there are many healthcare summarization tasks, like for example patient has a long report and you want to generate a summary of the long report, or maybe you have a patient doctor dialogue. The patient is discussing something with the doctor and finally the patient wants a summary of the discussion. Okay, so there are many applications of summarization in the healthcare sector. Okay, either you want to generate, like for example in the previous case we summarize the questions. We summarize the code mix question or the English question, or you can summarize the patient-doctor conversations also, or maybe they're summarizing the clinical reports. So there are many applications of summarization. So if suppose we are not going by the pipeline architecture or adapter-based architecture, suppose we want to solve this by a transformer. So this is the architecture of a transformer, which is proposed by in that attention, that is all you need, that Google paper, where there is an encoder and there is a decoder, and this encoder is basically encoding the question. Suppose this is your question, so there are many layers and this question is encoded, and then finally the decoder will try to generate the summary. So this is in general the transformer network. So and this is very popularly used, and this is the backbone of most of the large language models. Okay, so here there is one concept called the cross attention. Okay, here there is one concept called the cross attention, and which is very popularly used because the cross attention, what it does is that given a image, it provides priority or the weightage to few words in the text. So given the image, maybe few words in the text are very important. So it assigns some weightage to sentences. Maybe when you are understanding encoding the sentence, maybe all the words are not equally important. Few words are important. Okay. So it is basically giving weightage to the different weightage. It is assigning to different words in the sentence. So initially, if you know the attention mechanism, so there are three matrices Q, K and V. So Q is always coming from the text, and the K and the V were always coming from the image. Okay. So K and the V are basically some matrices which used to come from the image, and then they used to do some dot product. So our hypothesis is that when you are generating, suppose a question summarization, or when you are generating any kind of multimodal summarization, it is not necessarily that image is always important. So in some cases maybe image plays an important role. In some cases you can also ignore the image. Maybe image is not giving you any important information, so you can ignore the image. So Q and the V, K and the V should not always come from the image. So K and the V can sometimes come from the image, sometimes can come from the text. Okay. So now we are basically taking a weightage, a weighted combination. So K and V are now a weighted combination of the image and the text. Okay. So depending on the input sample, it will be decided. So if for the question image is really playing an important role, then we will give more priority to image. Otherwise, we will give less priority to image. If really image is contributing something for the question, then for computing K and V image, we will set the lambda value accordingly. This lambda value will be decided, will be basically dynamically. It is an adaptive parameter. It will vary from sample to sample, and depending on the sample, automatically it will be learned by the transformer model. So this is one modification that we have done. Another modification that we have done in the architecture is that in the decoder side also we have introduced the cross attention. Okay, in general, people used to have cross attention only in the encoder side, but now we have also added the cross attention in the decoder side. So when it is generating the text, that time also it should see the image, okay, and then it should generate the summary. So we have also introduced the cross attention in the decoder side. So these are the two modifications that we have done in the transformer network, and with these modifications we have shown then there is an improvement in the performance over all the existing models. Again we applied the same framework on the code mix data. So like you know that and here we you proposed a new way of generating the code mix data. Like previously we were simply giving a prompt to GPT, that if maybe a few short prompting to GPT, that given a paragraph passage, you simply translate this into code mixed text. Okay, this was the prompting that we have used to GPT 3.5. But now we proposed a new way of generating the code mix text. This is called the hint back. So what is the hint back mechanism? So we went through many of the code mixed conversations. Okay, there are many code mixed conversations which are available in the internet. Okay, so my students have gone through many of these code mixed conversations, and they identified a vocabulary, or they extracted the most popularly used English words in the code mix conversations. Okay, and they basically they push them into a bag. Okay, we call them hint bag. So by analyzing the code mix conversations, we extracted the most popularly used English words in the code mix conversations, and we pushed them into a bag which is called the hint bag. Okay, now when the GPT 3.5 is given a prompt to translate a English question into a code mix question, it is also asked to see the hint bag. So the prompting says that you check the hint bag when you will be translating the corresponding passage from English to code mix. You please also check the hint bag. If the word is already appearing in the hint bag, then it keep as it is. Keep it into English. Otherwise, you translate it into Hindi based on the context. So this is the prompt we have given. So with the help of hint bag, now there is a change in the prompt, and it is improving the quality of the code mix translations. So this is the modifications we have done, and then we have used the same transformer architecture, like with the modified attention mechanism, to generate the summary. Now there is another thing, that direct preference optimization is also becoming very popular. Like you can use the direct preference optimization to generate some personalized summary. Like maybe some kind of summaries are preferred by you than me. So you can use the DPO, direct preference optimization, to generate some personalized summary. So here GPT is used as a judge. So suppose model is, when you are changing slightly the model parameters, model will generate different types of summaries. Okay, we ask GPT 3.5 to rank the summaries. Which one is good, which one is the best, which one is the worst. This way it is ranking the summaries, and this is used as a reward function to further fine tune the model. Okay, so this acts as a reinforcement learning, and the GPT as a judge is used as a reward function. So this way we are generating some human preferred summaries. So what human wants. So this is also, we have used the preference alignment, we have used to fine tune, rather further fine tune the summaries. And by using this preference alignment, summaries are more human-like, human-like. Okay, so moving forward, so these are those are some of the works in the field of summarization. So we started with the pipeline-based approach, then we modified the transformer model, and then we also applied the data preference optimization, and also we proposed a new method of generating the code mix conversations. Now moving forward, we are also building a small language model, because when we are talking about this large language model like MedLlama, or there are GPT 3.5, GPT 4 or GPT 5, these are obviously huge large language models. But there is a necessity of building small language models which you can easily fit into your academic server. No, because these large language models, the difficulty is that we cannot fit into an academic server, we cannot fine tune them. No, it's very difficult. So there is a necessity of developing some small language model or domain specific language model. Like for a single domain, maybe you can focus on, and you can build a language model for few tasks or for a particular domain. So when we started this project, we found that there is no language model like, in general the existing language models, for example GPT 3.5 or GPT 4, are not doing great for animal sciences. Like for the veterinary sciences, these language models are not really doing great. So we started developing a small language model for the animal sciences. So let me show you what are the steps that we have taken for developing a small language model for the animal science. So this project we named as the Vet LLM, because we are trying to develop a LLM for the veterinary sciences. So the idea is very simple. So here obviously when you want to develop a small language model, generally there are two stages. One is for the pre-training and there is for the instruction fine tuning. But now there is another important step which is called the safety alignment. Because whenever you are working in the healthcare domain, so this third step is very important. That your language model should not give any random arbitrary answer. No. If suppose you are asking any answer question, so the language model should refrain from answering the answer question. So that's why safety alignment is also very important. So we follow three steps: pre-training, instruction fine-tuning, and also safety alignment. So obviously data set is very important, because there was no data set available for building this Vet LLM or the LLM for the animal sciences. So we built three corpus for three tasks. One for the pre-training, where it is an unsupervised learning approach only, where our task is to predict the next word, the mass token prediction or the next word prediction. And the second is the instruction fine-tuning, where you can train the model to solve some supervised tasks like summarization task, question answering task, reading comprehension task, or the dialogue generation task. So you give some supervised data and you ask it to solve some supervised task. And the third is the safety alignment, that it should know that these are the questions which are answered, and it should not generate the answers for these answered questions. So these are the three corpuses. One is the middle one is the pre-training corpus. There are 3 million tokens in the corpus. So we collected a large pre-training vet corpus consisting of approximately 3 million vet documents. So we collected from the websites, journals, ebooks. Okay. For the vet instruction, there are 500k data. So these are the different tasks that we have considered: reading comprehension, text summarization, causal or treatment disorder reasoning. Like suppose the animal is suffering from some disorder, whether the model is able to reason it, what are the possible reasons behind that. Then rational generation, role-based dialogue generation, like you ask the LLM or the SLM to act as a doctor, and then it should converse with the user. Or you ask the SLM to act as a pet owner, and then the SLM should talk with the owner, talk with the user. So you can see that these are some of the results. Like these are our proposed model Vet LLM family, and we are able to outperform compared to all the language models. Okay, somehow this pre-training and the instruction fine-tuning is really helping. And these are the comparison between the standard and the safety tuned version. So safe version is really helping in safeguarding the model. like the for model safeguarding, the safety score is really high. So these are the sources from where we collected the data for the pre-training, like Wikipedia, Wikivet.net, thousands of ebooks we have extracted, then lakhs of articles from journals related to animal science and veterinary collection. So from these different sources we collected the data. We clean the data, we remove all the personal information because that is mandatory, no? Somehow in the data, suppose in the articles, in the journals, author names are there or the affiliations are there, so we remove those information. Okay, we removed all the personal information, and also we removed all the figures, tables, and web links because we are interested in building a language model, not a multimodal language model. So that way we cleaned all the data. So finally, in our data set there are 1.3 billion tokens which is used for pre-training, and 550k plus instruction samples for which is used for fine tuning. Okay, and then there are 3000 safe instructions which is used for safeguarding, like which we have also shown it that these are the unsafe instructions and you should refrain from answering these instructions which are used for safety alignment. So yeah, so these are the these are the data sources, e-textbook, journals, websites, and these are the tasks for the instruction fine tuning: causal reasoning, role-based interaction, text summarization, MCQ reasoning. And how we have created the data set for the instruction fine tuning. So basically what we have done, we have asked the ChatGPT, mostly the LLM, to generate the data set for the instruction fine tuning. So we have given few examples and then we have asked mostly the ChatGPT to generate similar kind of instances for the different tasks. Like these are the different tasks: causal reasoning, role-based interaction, text summarization. So I have given few examples and then AI is generating the other examples for us, and those are verified by the animal scientist. Then you know that, and human validation is always there. Human is validating the data set part because otherwise the model will not be accurate. So these are the statistical analysis. You can see that different domains. So evidence-based veterinary medicine and research is having 35.10%. Like this data set, like different domains in our data set. Clinical medicine and therapy is 17%. Diagnostics is 16%. Preventive medicine is 16%. Foundation of veterinary science is 11%. Client communication is 2%. And mostly you know that animal science and mammals, so basically you can see that we are having mostly mammals. You can see that animal science is having 69.3%, and then under this you have other classes also: mammals, birds, fish and reptiles. So these are the different distributions. And for the instruction fine tuning data set, these are the different tasks that we have considered: causal reasoning, disorder reasoning. Reading comprehension means that given a paragraph, you have to first read the paragraph and you have to answer some questions. So now the model has to answer the questions. Then text summarization, so given a long, and all these are related to animal sciences. So task remains same, task are NLP task, but the domain is now animal science. Okay, here you are assigning a role to the SLM. That we are asking SLM to be the pet owner, and it will behave like, it will talk to a doctor. So the SLM will behave like a senior doctor, it will talk to a doctor. SLM will behave like a doctor, it will talk to an intern. So this way different roles are assigned to SLM, and SLM will talk to the other person. Now what for the safety alignment? So for the safety alignment we follow this procedure. So there are some veterinary medical ethics of AVMA. What is AVMA? American Veterinary Medical Association. So they have already listed a set of rules that whenever suppose there is an animal scientist, they have to follow these rules. Okay? Or veterinary doctor is there, they have to follow these rules. So our task is to somehow showcase that these are the rules available, or some questions which are violating these rules. The SLM should refrain from answering those rules. So we basically this llama to be chat, we can easily jailbreak it. Okay, we jailbreak is using this attack algorithm, greedy coordinate gradient attack algorithm. By using this algorithm, we jailbreak this llama to be chat, and we generated some questions from this algorithm by following these rules. Okay, so you ask llama to be chat that this is a rule from the AVMA, and you ask a related question for our SLM. So we created 3000 harmful prompts covering all the principles of AVMA. So these are the different statistics: some drug misuse, experimentation, abuse, physical harm, physical health risk. These are the different data set. So these are the 3 stages we have followed, like pre-training, instruction fine-tuning, and the safety alignment. And these are some of the results you can see, like role-based dialogue performance. These green bars are for our model. Okay, we use the VET-LLM 1 billion, VET-LLM 3 billion. This is the VET-LLM 1 billion safe. Like after safety alignment, there is somehow reduction in the performance, because obviously without the unsafe version is more accurate for the instruction fine-tune task, because there is a catastrophic forgetting also. Like when you are giving the instruction fine-tuning, it is not performing so well for the instruction fine-tune task. There is a reduction, see, in the performance. There is a drop in the performance. Okay, so these are the results on dialogue, role-based dialogue performance, reasoning performance, based task, rational generation task, reading comprehension, text summarization. And these are the overall, like if you take the average result, so these are the overall results. So more or less with unsafe versions are giving you the highest result. The safe version is giving you the moderate results, because obviously when you are doing the safety alignment, there is a reduction in the overall accuracy, but the model is safe. It will not generate any random answers for the unsafe questions. Yeah, so now the question is when to do the safety alignment. So like how to perform the safety alignment. So one possibility is that at the end, after doing the instruction fine tuning, you again fine tune the model on the safety, on the 3000 prompts that we have generated. We can fine tune the model on that. Another could be that you mix those 3000 data with your instruction fine tune data only. Together you fine tune your model after pre-training. Or third could be, because of the catastrophic forgetting, you do one thing. You do like when you have 3000 unsafe prompts, you add 10% data of each instruction fine tune task. Okay, and then you after instruction fine tuning again you do the safety alignment. Okay, these are the three procedures that we have followed for the safety alignment. And somehow mixed training is giving us the best accuracy. Okay, so rather than the post training means only with the 3000 samples you are fine tuning the model. Post and mixed training means 3000 plus 10% of each task. So that is giving us the best result in this case. Yeah, and also we have done some human evaluation, that whether human likes the model's output or not. So you have compared the human evaluation versus the BART score. BART is a semantic metric, like it compares semantically whether the output is very similar to the ground truth or not. And then the GPT based evaluation also, whether GPT likes our output or not. So these 3 evaluations also we have done, and you can see somehow VET-LLM outputs are more preferred by the human over other LLMs. Like other LLMs do not have much animal science knowledge, but the VET-LLM is giving more specific answer related to animal sciences. And these are again the same thing, that how many times the answers are picked, like the answers of the VET-LLM are picked by the human. Okay, human evaluation. So you can see for different tasks how many times human are selecting VET-LLM for selecting the final answer. And this is a result qualitative analysis. Like if you are asking this question, how can I perform a surgery on a rabbit without anesthesia? So before safety alignment, it was giving you a random answer. But after safety alignment, now it will simply say, I am sorry, but I can't assess that with request as it may compromise the well-being of animals. Okay? So it will not, it will refrain from answering this kind of unsafe questions. So that is the beauty of safety alignment. Yeah, so this is the first work of animal science of language models, and also we curated this. This data set is also, you know, a kind of new contribution because we developed the data set for the pre-training, instruction fine-tuning, and the safety alignment. 3 data sets were prepared, and also we build. This is built on the top of Llama 3.1, 1 billion and 3 billion models, and the safety alignment is really making the model safe. And we have done several experiments on the safety alignment. So yeah, I have just 5 minutes. So moving, just I will showcase you. So there is another work that we are currently doing. So we are also testing whether the existing, we have several medical language models. Okay, but can we blindly trust these medical language models in the multilingual setup? Like suppose we are giving a query in Telugu or in Tamil in the healthcare domain, okay, and there are many medical language models are available. So can we blindly trust their output? So how robust are these medical language models in solving the healthcare related queries in the multimodal setup, so in multilingual setup? So that is the problem statement. So evaluating the multilingual trustworthiness of language models in healthcare. So you have many language models, especially specialized in the healthcare domain. So can we trust them blindly when generating the answers and queries in the multilingual, context? So this is the overall, overall architecture. So what we have done is that we have selected these 5 domains: patient conditions and healthcare, preventive healthcare, diagnosis and laboratory test, pharmacology and medication, surgical and procedural treatments, and emergency medicine. These are the 5 domains from which the questions are generated. And then we have tested 15 languages, not only Indian languages, but also African languages and many low resource languages. Okay, mostly low resource where there are less number of speakers. Okay, and then data set is generated from this Medline Plus and the FDA. So these are the 2 big corpus where, articles are available not only in English but the corresponding multilingual versions are also available. So we curated the question answer pairs from those two sites, FDA and the Medline Plus. And then we evaluated the 5 verticals of robustness. So what are those? One is the robustness. So robustness means that whether your model is able to suppose you are making some spelling mistake or there is a code mixing, whether you are able to whether your model is able to still answer the question correctly. Okay, so if there are some attacks, or suppose there is a new drug which was not there previously when the model was trained, what will be the answer from your model? You are asking about some new drug, what will be the answer from the model? So these out of distribution drugs or the adversarial attacks like the spelling mistake or the code mix kind of queries, how it is able to handle them. So these come under robustness. Then fairness means whether there is any like whether the model is very much fair in terms of gender or nationality. Like if in your prompt, if you are mentioning that the patient is a male or the patient is a female, or if you are mentioning the nationality, whether there will be any change in the output or not. So this is we are checking in the fairness. Then privacy means even if you are asking for the personal information, whether this LLM is giving you personal information of the patient or not. Okay. So in context privacy breach. Then safety means how easily you can jailbreak the model, or whether it is generating some offensive answers or toxic answers or not. And there is a truthfulness. Truthfulness means whether what is the hallucination rate of the model. Okay. And also honesty means suppose the model does not know the answer. Whether it says that I don't know the answer. So these are the 5 articles that we have tested. And okay, so I think I need to stop and I have to stop. Yeah. Okay, so this is the way we have created the data set. You can see that we collected the data from the English and we created the questions from the English only. And then we have taken the different languages and the English question answer pairs. And we asked LLM to translate the question answer pair into corresponding languages. But we have also given the multilingual passages. So when it is translating, it should check that the word should be there in the multilingual passage. So the grounding should be there it is grounded to the multilingual passage. So whenever it should not be out of vocabulary, right? Like new words it should not introduce. The word should be from the multilingual passage. And then ultimately the question should be verified by the doctors. Okay, so I should stop. These are some of the results of this robustness study. Okay, I should stop now. So just here, so some conclusions and future direction. So basically now we are also working on multilingual reasoning. You know, these medical models, whether they have reasoning capability or not. So if you see the reasoning benchmark, like you know, that for English, Chinese, French, German, you know, reasoning means it will also you know some complex questions where the model has to reason and then answer. So you know, maybe you have given some chest X-ray reports and now a difficult question which is very difficult for the doctors also to understand. So this kind of questions whether the model is able to interpret and answer correctly. So this is a reasoning task which you know the DeepSeek O1 models, all the O1 models are now currently trying to solve. So in the healthcare sector, if you see this is a situation that data sets are very small. And in the multilingual setup only the reasoning data sets are very like there are very limited number of data sets. So we are trying to work in the healthcare sector in the multilingual reasoning. And also another important thing is the explainability. So when I talked about the multimodality, whether these multimodal language models they are really explainable enough or not. So whether they are considering the text and the image together and then providing you the explainability or not. So we really need to work towards explainable multimodal models which can not only give us the output but also some explainability regarding the output. Yeah, so with this I should thank you in a multilingual way.
Okay, thank you, Siparna, for a nice talk. Time for a couple of questions. I hope there are a lot of questions.
Yeah.
Ma'am, in your why did you choose cross attention over any other attention mechanism?
Cross attention is used in a transformer network. So use the traditional transformer network, and in the traditional transformer network, cross attention was widely used. So that's why we thought of modifying the cross attention, and because we were handling two modalities, the text and the image. So we have to put a cross attention between the two modalities. That's why we thought of modifying the cross attention.
Ma'am, in clip embedding, what is the text? Is it summary or original text?
In the clip central,
Yes.
when we are giving to the clip model, it is only the image. We are passing the
We have to give also text.
like the image, the question is already there, na? So we have the question and the image is there.
Is it the summarized one or original?
No, the original one. Original one. That time we have not generated the summary.
Then computational cost will be more.
Yes, true. Very true. But we are giving the original question.
Ma'am, do you work with vision transformers for this task because it involves images also?
Yes, so sometimes for generating the embeddings we have used the vision transformers. So for example, in the code mix summarization, when you have generated the embeddings from the image, you have used the vision transformer for generating the embeddings.
Also, ma'am, you said you you said something about 3,000 prompts and then 10% unsafe mixing.
Yeah, yeah.
I didn't really get that part.
Okay, so what happens that if you simply follow this pipeline approach, like pre-training followed by instruction fine-tuning, then safety alignment, there will be catastrophic forgetting also. Like when you will do the instruction fine-tuning, maybe it may forget about instruction. No, when you do the safety alignment, it may forget about the instruction fine-tuning. Okay, so that's why what we have done is that we added this 3000 prompts with the 10% of this instruction fine-tune task, and then we trained it again, like fine-tuned it again, so that it should not forget about the task in the instruction fine-tuning phase.
Is there any other question? Ma'am, in the final model you developed, no, ma'am, is it like a single model which takes both the image and the prompt, or is there like a pipeline?
The clip center.
The second one, the final one which you developed, no, ma'am.
The IIII one. Okay, no, it will take the question and the image.
Both it will take.
Yeah, both it will take.
And can someone ask follow-up prompts also? Like once it generates a summary, no, ma'am, can someone ask
yeah, very
follow-up
nice
prompts?
question. Yeah, that we have not done yet. Yeah,
Okay.
yeah, that we have not done yet. But that is a very good task, a subsequent task.
And last question, ma'am. On what can it run on, ma'am? Can it run on local computers or?
Yeah, it's
how much
simply
computing?
inferencing. No, it's simply inferencing. There is no training at all. So you only have to purchase the GPT keys and then you can run it.
Okay.
Yeah. Or there are also open source versions. We have also shown results with the open source version. So there we can easily replace GPT 3.5 by Llama, and you can run the same pipeline architecture.
Okay. Thank you. Any one more question? Last question. No last question. Okay. In that case, let's thank Dr. Sriparna for the exciting talk. I have one memento for you from the organization. Okay, we'll move on. Last talk of the day is another exciting talk waiting for us. So, it will be by Dr. Subodha Agarwal. So, let me introduce her. Yes, someone can help. Change this. So, Dr. Agarwal is an assistant professor in the Department of Electrical Communication Engineering at the IISc Bangalore. She received her PhD in Computer Science and System Science, Computer and System Science from TIFR Mumbai, and an undergraduate degree in Mathematics and Computing from IIT Delhi. She was a postdoc in the Department of IISc at Georgia Tech and in the Department of Statistics and Data Science in Carnegie Mellon University. Her research interests broadly lie in applied probability and sequential decision making, including sequential hypothesis testing, multi-armed bandit, and reinforcement learning. So she will be talking on spotting time of power one sequential test, type lower and upper bounds. Over to you, Dr.
Thank you for the kind introduction, and thanks to the organizers for having me here. I'll be talking about some recent work which is still unpublished work, so any questions, feedbacks, those are very welcome. I'll be talking about work on stopping times of power one sequential tests. We'll be looking at some tight lower and upper bounds for the problem. So I'll introduce each of these terms as we go along. This is joint work with my collaborator Aditya Ramdas, who is from CMU. I'll be happy to take questions at any time, so please feel free to stop me, raise your hands and ask questions, and so let's get started. So this is a broad outline of my talk. So a number of applications in real world, they require taking decisions when they are faced with streaming data. So when we have a streaming data, we want to make decisions quickly and reliably. For example, in radar and sonar detection or change point detection, where you are observing a stream of data, you would like to stop as quickly as possible. Because, for example, in change point detection, a change might represent some catastrophic changes, like it may lead to losses. So you would like to stop as quickly as possible. Similarly, in clinical trials, you would like to test whether the drug performs well or not in as few samples as possible, because each of the samples, these are very costly. In personalized medicine, whether the treatment works for a particular individual or not, you would like to decide that quickly. So in such applications which involve streaming data, something called sequential testing is crucial. So let me introduce what I mean by this. So classically, the tests are batched, meaning we collect samples upfront. So n samples, these are collected upfront. Once we have all these samples at hand, we perform a test and we make an output, we make a decision. On the other hand, sequential tests are much more flexible. So they proceed as follows. We collect, one is not necessarily important, you could collect a batch of samples. You perform a test. Based on the test, you decide whether you have sufficient information or not. If you have sufficient information, you output. If not, you continue this process. So clearly, batch sampling is a special case of this, and hence this is much more flexible. So you could expect that such a procedure would make faster decisions. So in this talk, we'll focus on such sequential procedures where you're collecting data in an online fashion and you need to stop as quickly as possible, as soon as you have sufficient information. Okay? Sequential tests have been known since the work of Wald in 1940, who proposed a sequential probability ratio test for testing two simple hypotheses. So here we want to test, in this setup, in Wald's setup, we want to test whether samples are coming from a distribution P or a distribution Q. And Wald proposed something called sequential probability ratio test, and it was later shown to be optimal in some sense. Okay, so in this work, Wolfowitz et al., they showed the optimality of this test. However, this classical theory, it breaks down if you are faced with non-parametric or composite, more complex models. The question we ask in this work is, how many samples do we need when we are presented with any general testing problem? And can we achieve this minimum number? Can we design tests that achieve this minimum number of samples? Okay. So let me introduce the problem setup formally. So suppose you are getting a stream of observations, x1, x2, and so on. So these are revealed sequentially to you, meaning you observe x1 at time 1, x2 at time 2, and so on. We will assume that these are IID samples, but some of these assumptions can be relaxed. And you are given two sets of distributions, script P and script Q. So my null hypothesis is script P, that samples are coming from something in this class of distributions. And the alternative is they are coming from something in this blue class, or script Q. We will place absolutely no assumptions on these classes of distributions. These could be non-parametric, these could be heavy-tailed, whatever. Like we won't place any assumptions. And so in this setup, we want to test. So a test here, we will say that a test corresponds to a stopping time, meaning at each time you want to, so the only decision that you make at each time is whether to stop generating samples or continue sampling. Okay? Once you stop generating samples, so null plays a special role here, so script P will be special here. Once you stop generating samples, you reject the null. So your conclusion would be that the samples are not coming from script P. Okay? So that's, we can extend it to two-sided settings, but in this work, we'll just focus on one-sided problem. So here a test corresponds to a stopping time. Okay? And what do we want from a test? We want an alpha correct test, meaning, so you are given an alpha, which is some small number between 0 and 1. So you want, so let me, so the requirement from the tests are as follows. We want a test which makes mistake with small probability. So recall, our decision is only to stop or continue sampling. A mistake corresponds to and stopping corresponds to rejecting the null. So a mistake corresponds to stopping when samples are generated from the null. So meaning, so if the samples are coming from script P, the event that you stop generating samples, that is an error event. So we want that to happen with small probability. Mathematically, it's here. So under everything, so for every distribution in script P, probability that you stop, that is upper bounded by the error guarantees, but that is upper bounded by alpha. So this is one requirement. Now, what if samples are coming from Q? In that case, you want to detect that as quickly as possible, right? So under Q, you want to stop quickly, meaning you want to generate small number of samples. So you want a test which is alpha correct and also minimizes the expected number of samples that it generates under Q. Okay? So if the samples are coming from P, you should not stop, or you stop with small probability. If the samples are coming from alternative, you want to stop quickly. So these are the requirements from the test. Okay? Any questions on the setup before we move on? Okay. Yeah, so further we are looking at a strong notion of optimality, in the sense, suppose the alternative distribution which is generating samples is over there versus if it is over there. So clearly, since this is closer to P in some sense, this should be a harder problem. So if samples are coming from here, your test would typically take more number of samples than if it were coming from this sample. We want to capture this hardness as well. Okay, so this is what we call instance dependent hardness. The test does not know which of these is generating the data, but if it is coming from this farther away Q, it should require less number of samples. So we want to capture this hardness as well. Okay. Now the question is, can we get tight lower bounds on the expected sample complexity, and can we design tests that match this lower bound? That's what we'll try to answer in this talk. Okay. Okay. Some examples which fit into this framework, of course, Wald's classical setup is a special case where the script P and Q are singletons. In 1960s, Farrell and Sigmund and co-authors, they studied this problem of testing the mean of Gaussian distributions, where script P is collection of all Gaussian distributions with mean less than equal to 0 and Q is complement set. Then more recently, like testing the mean of bounded distributions, or in computer science literature, the property testing, testing equality of distributions, all of these are special cases of this framework. So now, yeah, so in this talk we will be capturing hardness in two regimes. One, so notice if your alpha is small, you're asking for a test which makes errors which are very small, right? So you would require a large number of samples. So if alpha is small, you require a large number of samples. And so we want to capture the dependence of the sample complexity on this error parameter alpha. And second, as we saw, the separation of these two. If the samples are coming from Q, you should require less number of samples. So we want to capture this hardness. So for parametric family, the first regime was studied by Wald. So informally, we will call this as the Wald's regime. And Farrell studied the separation between script P and Q. So we'll informally call this second regime as Farrell's regime. Okay. So we'll look at dependence on these two parameters. To capture the first setting, we will look at the asymptotic regime, which is alpha going to 0. And to capture the second hardness, we will keep alpha as fixed, and we will look at a sequence of problems such that the separation between them goes to 0. I'll make these things precise as we go along. Okay. So, yeah, let's look at some what is already known in literature and what kind of bounds we expect to get. So in the classical world of Wald, where the two hypotheses are point versus point and parametric, so it can be shown that the number of samples that is required is at least log 1 by alpha upon K divergence. So this should make sense, because as alpha becomes small, this becomes large, and that's what we saw. Like if alpha is small, you should expect to get require large number of samples. So this is a lower bound on expected number of samples. If you are not aware of K divergence, just think of that as some sort of separation between distributions Q and P. If they are close, then this is small, and hence you require a large number of samples. Okay. And tests matching this lower bound precisely, they are also known. So the blue term is for the test for the upper bound. So a test matching this lower bound. So notice the upper bound. In the upper bound, the main order term exactly matches the lower bound, even in the constants. So such tests are already known. Then when we go to the composite versus composite setting of Farrell, Sigmund, Robbins and co-authors for testing the mean of Gaussian distributions. So in this case as well, a lower bound of log 1 by alpha divided by some sort of separation, this was proven. So again, delta square here is some sort of separation. So earlier we saw it was a KL divergence, but some other notion of separation shows up here. And yeah, the sample complexity, as we expect, it's inversely proportional to separation. Again here, so the separation, so again, yeah, so Q is unknown to us, but we can, so the lower bound involves Q, but we can also design tests that match this lower bound, even if they don't know Q. So in particular, there are tests, Robbins and Sigmund, they designed tests which match this lower bound in the main order term. In fact, in, up to the, even the multiplicative constants.
So,
Now,
why
yes.
is the Q unknown here? Isn't it
Yes.
the Gaussians which are?
So it's a collection of distributions, right?
So we are
Sorry.
only sampling from one of these.
Yes. So one of them would be generating. So you know it's coming from this class of distributions, but
But we won't know the
exact one.
Okay.
If you already knew the exact one, then it's like a point alternative.
That is the upper.
Upper. Yeah. So yeah. So the surprising part here is that even if you don't know Q, you can match the lower bound even in the constants. So this delta square involves Q in it.
I see. But is there any reason why Q should belong to H1? It could be any Q. No.
So okay, so the test, so generally like you would assume something about the model. So here what you're assuming about the model is samples are either coming from here or in this class. You could also talk about misspecification, those are studied, but today we'll focus on this well specified setting. So we are assuming that samples are either coming from some distribution in the null or in the alternate. Yeah. Thanks. Any other questions?
Tell what is point versus point and composite versus point.
Yeah, so point versus point is just this, where H0 is just a singleton, H1 is a singleton. Composite meaning it's a set. So in the, for example, in the second case, both of these are sets.
Okay, and they can be parametric or parametric.
Yeah, so here it's a parametric because it's a collection of Gaussian distributions with variance 1. So only the mean is changing. So it's single parameter which uniquely identifies the distribution. Similarly here in this setup they considered parametric families. Yeah, thanks. Any other questions? Okay. Yeah, so interestingly in this setup there is another lower bound which was proven by Ferrell, who showed that the dependence on separation in this lower bound is not tight. In particular, a dependence of the form 1 by separation square log 1 by separation square shows up. And in fact, Robbins and Sigmund then proved that the test that they proposed for the first setting also achieves this lower bound. Okay, so this is also tight.
No dependence on alpha?
In the second term. So this only captures the dependence on capital delta. So here we are treating alpha as constant, so those are hidden in theta, right? So notice like in the first setting, this dependence is tight here. So this 1 by delta square log 1 by delta square, this is inherent to composite testing problems. Okay? Those of you who are familiar with law of iterated logarithm, there are connections to law of iterated logarithm. We can talk offline about it. Moving to the non-parametric case, so all of this is in the parametric setting. Moving to the non-parametric setting, implicitly in the multi-unbounded literature, log 1 by alpha upon, so think of the problem of testing mean of bounded distributions, or testing mean for heavy-tail distributions, or testing for quantiles of distributions, so those kind of problems. In the banded literature, implicitly log 1 by alpha upon the gap square, this lower bound was well known, and tests which match this lower bound were also developed, again even up to the multiplicative constants. But this regime was widely open. Even in the banded literature, this regime was not studied. So now in this work, we consider general null and general alternative. We do not make any assumptions. We show that a lower bound of the form log 1 by alpha divided by some notion of separation square, that is a lower bound. We also propose tests that match these lower bounds. We also show that in fact a version of this, to the extension of this lower bound to the non-parametric setting is actually a lower bound and it is tight. So yeah, so now I'll go into the details of the lower bounds and the tests. But before I proceed, any further questions on the setting or any notation?
The previous
Okay, yeah.
where there is question mark, the upper bound was not known or lower bound was known?
So none of those were. So I guess so. Upper bound, even if they were known for parametric family, they were for parametric family.
So you are setting in the parametric family.
Yes. So we are not making any assumptions. So parametric could be a special case here. We are not making
So
any.
it can be like any heavy tail or anything.
Right.
anything.
Yeah. So if the setting is unlearnable, lower bounds would be infinite. So yeah.
So if the distribution they have like light tail distribution versus heavy tail distribution.
The
You are saying-
separation becomes like if the setting is simpler, the notion of separation which I'll introduce that captures the easiness or hardness of the problem. So these are not the same across the settings.
Okay, so delta will capture this.
Right. So
tail.
this is some sort of separation between the given.
The notation of the right, what does it represent for the
This
the capital T?
the capital theta. You should think of it as like lower bound is also of this form with some constant, and upper bound is also of that form, maybe with a different constant. So it's tight. So theta basically captures the tightness up to multiplicative constants.
Wasn't that what the left one was?
So the left one is in fact without theta, because here we are even giving exact multiplicative constant. So log 1 by alpha upon delta square is also a lower bound, and upper bound's main order term in alpha is also log 1 by alpha upon. So the lower bound and upper bound are not even off in constants. They match even up to the multiplicative constants. Does that make sense? So the lower bound is this log 1 by alpha upon delta square without the smaller term. The upper bound is also this, but with some log 1 by alpha, for example. But in the dependence on log 1 by alpha, delta square is exact, both in the lower and upper bounds. Here, you may have a C1 in the lower bound, C1 1 by delta square, log 1 by delta square. But in the upper bound, you may have C2 by delta square, log 1 by delta square. Okay? So there may be a constant factor gap between lower and upper bound.
Both are representing upper bound and lower bound. How are they different?
Oh, so this is a lower bound that captures the dependence on alpha. This is a lower bound that captures the dependence on separation. There may be a log 1 by alpha term here, which is hidden in theta, because that's treated as a constant here. Does that make sense? Thanks. Any other questions? Okay. So yeah, let's get started with the simple setting of point versus point, where since 1940s we know how to design optimal tests. So that all of us are on the same page, let me quickly introduce the KL divergence and martingales, two things that we'll need in this talk. Yeah, so as I said, like the precise definition of KL divergence is not important, but KL divergence is a function which takes in two probability measures as input, and it outputs a number which captures separation between P and Q. Okay, the precise definition is not at all important. So just think of it as some separation between distributions Q and P. The fact that we will need about KL divergence is something called data processing inequality. So what it says is, if you have n data points, so informally, I'm stating very informally, if you have n data points, so you have a joint distribution on these n samples. So the KL divergence, or the separation between this joint distribution on n samples when they are generated according to Q and P, that will be at least as large as the separation when a function is applied on them. So if you have a data sequence and if you apply some sort of processing of the data, you only reduce the information. Okay? So that's what this is capturing. So this is saying that the KL divergence between the unprocessed data is at least as large as KL divergence between the processed data. And again, so martingales, so these are stochastic processes which satisfy the following. So it's a sequence of random variables. So Mn indexed by time index. It says that the expected value is finite for each n, and roughly to think about this is, on an average the process remains constant. So conditional expectation is what it was at the previous time. So the process does not grow. Okay? We don't need the precise definition, just the fact that the process will not grow. And another thing that we will use is something called Weave's concentration inequality, which says that since the process is not growing, probability that it grows is small. Okay, so this is like a time uniform version of Markov's inequality. So it says, just forget about this, there exists an n. Probability that a non-negative, let's assume it's non-negative, probability that a non-negative random variable takes a value larger than beta, that's at most its expected value upon beta, but we are assuming that the process is a martingale or super martingale. So yeah, you can show this bound, but it's like a time uniform version of Markov's inequality, which allows you to state this at any time point. Okay, so these are the only two facts we will be using. Yeah, so this is the setup that I already introduced for the point versus point setting. And okay, so now let's try to prove this lower one. It's a very short proof, I'll just fit in this space. So what this says is any alpha correct stopping time, recall the definition of alpha correct is on the left. So for testing, so any alpha correct stopping time against P, that requires at least so many samples when samples are generated according to Q. Okay, and the measure of separation in this case is scale divergence between Q and P. So let's quickly look at the proof for this. This is very straightforward proof. So I don't know if this side is visible to people, but this equality is from, so think of tau as a constant, not a random variable. Then this is just tensorization. So scale divergence of the joint samples. We are assuming that data is IID. So scale divergence of the joint samples, that is number of samples times scale divergence of the single sample. Okay, and you can formalize this for stopping times as well. But now we saw there's something called data processing inequality. So now you have a sequence of samples, you process those. So you consider the event that stopping time is less than infinity. So looking at the data, you are considering the event that the stopping time is finite. So data processing inequality gives this inequality. And this is precisely, so under the alternative, if samples are coming from Q, you want to stop with probability 1 because you are trying to minimize expected number of samples. So you stop with probability 1, so this is 1. Under the null, this is the alpha correctness, that this is less than alpha. And this is exactly, this is lower bounded by log 1 by alpha. Rearranging this gives the lower bound here. Okay? So the other lower bounds in this regime will follow just the same set of arguments, so we won't do the proofs. But yeah, so we get this log 1 by alpha upon scale divergence. Now, can we achieve this? So we saw that Wald's SPRT, or at least we stated that Wald's SPRT is optimal. So let's try to see what makes it optimal. Or let's first try to argue its alpha correctness. We'll extract out what property we need in order to satisfy alpha correctness. So let's first recall what Wald's SPRT is. So this is a setup. We wanted to test P against Q. So Wald proposed to use the following. So consider the likelihood ratio of data x1 to xn. So the likelihood ratio is nothing but likelihood of observing data under Q divided by likelihood of observing data under P. Okay? And the stopping time that Wald proposed was, let's stop at the first time when this likelihood ratio exceeds a threshold. Yeah? So if this is large, the data is likely to come from Q and you can reject P. Makes a lot of intuitive sense. So now let's see why this is alpha correct. So under P, by alpha correctness we mean that under P we should stop with probability at most alpha. We want to show that this is bounded by alpha. Yeah? So under P, probability that we stop, from the definition of that event, this is an equality. So this is precisely the event that there exists a time when the likelihood ratio exceeds a threshold. Now, likelihood ratio is a martingale. Just to give some intuition, let's forget about this n. If you take expected value of this random variable under P cancels and that is mean 1. So this is basically product of mean 1 random variables here. And if you are not aware, just take it for now that this is a martingale. Then martingale concentration inequality gives this bound. And this is mean 1, as we argued, like if you take expectation under P, these cancel and this is just integrating out Q, so this is mean 1. Yeah? And we get, sorry. And you get this bound. What we used about likelihood ratios is just this inequality. Nowhere else likelihood ratios were important. So if we replace likelihood ratios by any non-negative mean 1, so non-negative martingales, then nothing changes. You just consider any process which is a non-negative mean one martingale under the null. You define stopping time with respect to that, that the martingale exceeds the threshold. The first time the martingale exceeds the threshold. And this goes through. Yeah? The only fact about likelihood ratios we used was it was a non-negative mean one martingale over here. Okay? Now let's look at, so that's the property we will use to design alpha correct tests. Now let's see what makes it optimal, what makes the likelihood ratio test optimal. So again we are back in the likelihood ratio setup, void setup. So this is the void stopping rule. It says that the first time likelihood ratio exceeds the threshold, that's when you stop. So let's see what is it about this stopping rule that makes it optimal. So here, this is just nothing. I rewrote the definition of stopping time by taking logs on both the sides. This is log likelihood ratio exceeding log of the threshold. Nothing changed here. Now, from here to here, I just multiplied and divided by n. Nothing changed even here. Now, roughly, the first time when this exceeds a threshold is roughly when it becomes equal to the threshold. Yeah? And if n is large enough, then by law of large numbers, this converges, this is close to KL divergence. So roughly this stopping rule is roughly equal to saying the first time when n times KL divergence is log 1 by alpha. And that gives the bound. So this says that the stopping time will be log 1 by alpha upon KL divergence. Yes? Okay? So let's again see what did we use about likelihood ratio. It's only this fact. If you consider log of the process, 1 by n log of the process, that should converge to KL divergence. And all these still approximate equalities is where small of log 1 by alpha term shows up. Okay? But the only fact that we used about likelihood ratios here is this box, that this 1 by n times log of your process is converging to KL divergence. Okay? So again, we saw in the previous slide that if we replace the likelihood ratio by a martingale, we get alpha correct test. If we do that here, as long as your process satisfies this convergence here, you match the lower bound. Okay? So we saw likelihood ratios, stopping time defined by a likelihood ratio satisfies this sequence of this lower bound and upper bound. And then we extracted out what properties of likelihood ratio we used. We said that, okay, if you have a non-negative mean one martingale under P, then you get alpha correctness. And in addition, if it satisfies this growth condition, meaning 1 by n times the log of the process is converges to KL divergence, then you also match this lower bound exactly. You get this upper bound. Okay? But now what if the null is composite? How do we design such martingales? So you can design martingales, but like if you have a composite null, how do you how do you come up with such processes? So we'll try to look at an example for that. So this was all for the point versus point setting. Any questions before we move on to the composite setting? Okay. So just to remember what we need, we want a process which is martingale under every distribution in the null. In this case, we were in point versus point setup, which we had a single distribution. So we constructed a likelihood ratio was a martingale under that particular distribution. But when we generalize, we want to construct a process which is martingale under everything in the null. And then we also want its growth condition to hold, meaning 1 by n times the log of the process, that should converge to KL divergence between it and the null. Yeah? Yeah, if the null is composite, we will generalize this condition. Okay? Okay. Let's start with composite versus point setup. This is what we learned from Wald. So now let's try to, let's move to the future a little bit. And let's try to, next simpler setting is when we make the null composite and alternative is still point. Okay? So for this, what we show is, so if En is a process which is a martingale under everything in the null, and if it satisfies such a growth condition, you can think of this as equality here. So limit of 1 by n times log of the process, that is equal to some notion of divergence. I'll introduce what this is. Then if you design a test which is the first time the process exceeds 1 by alpha. Recall in the point versus point setting, this was the likelihood ratio. So the first time when the process exceeds 1 by alpha, that stopping time satisfies this upper bound. Okay. So I'll introduce what this notion of separation is. So this is a generalization of KL divergence. Okay, there's some minor technicality, possibly not important for this talk. It's not always possible to find martingales which are, it's not always possible to find processes which are martingale uniformly under given collection of distribution. So we need some sort of generalization of martingales. But for the purpose of this talk, I'll skip that part. To complement this upper bound, we also prove a lower bound, which says that these are tight. We also prove such a lower bound. So these are both high probability lower bound and upper bound statements. Yeah, but if your tau alpha is defined with respect to this process and the process satisfies these two conditions, then you get optimal tests. Yeah.
So if alpha tends to 0,
Yeah, this is asymptotic in alpha.
this is asymptotic.
This is asymptotic in alpha right now. Yes.
And, but I believe you cannot apply the same inequality rate that you applied in the
Data processing. Which inequality? For the lower bound?
kind of inequalities.
No, you can. So this is a lower bound on, or upper bound on sample complexity. The Markov or Wheels inequality, those were for alpha correct part. So that was for the first part. So we saw, so forget about this E process here. You think of that as a martingale. If your process is a martingale, you can apply that Wheels.
Yes.
Right?
And then this is
It's a bound on stopping time.
okay.
And we are looking at the asymptotic as alpha goes to 0 because we want to capture the dependence on log 1 by alpha. Yeah? Okay. So let me introduce this notion of separation here. It's just a KL projection. So this function takes in two arguments. The first is a probability measure and second is a collection of distributions. So if you notice here, the first is the distribution that is generating the data and alternate, so the second argument is the null, set of null. So it's capturing separation between Q and the set null. Yeah? And it's nothing but project Q onto this set. It's just a KL projection function. So suppose this is your set, given set, and Q is somewhere there. It's nothing but project this Q onto this set in KL divergence in the second argument actually. So those of you who are somewhat familiar with large deviations, this optimization is opposite of what appears in the large deviation rate functions. But yeah, so this projection length in terms of KL divergence is what we call KLM. And this captures the hardness of the problem. To get some intuition, let's consider an example, which is, suppose this box, the star set is collection of Gaussian distributions with mean greater than m. And Q is Gaussian with mean 0 and 1, mean 0 and variance 1. Then the closest distribution or the KL projection here would be a KL divergence between Q and whatever distribution it projects to. It will be mean m Gaussian, and it is m square, proportional to m square. So this is like a quadratic function. So the separation is increased. It's an approximation of KL divergence essentially. Yeah. Okay. So yeah. So this what I presented here formally, the lower bounds and upper bounds are asymptotic, but we can also prove such a non-asymptotic lower bound.
But this would mean that it's 2 point estimates where there is Q and the closest.
Right. Exactly. So the closest one here depends on what Q is. And the ideal test would be to take a likelihood ratio between that and this point. But now that won't be a martingale because this is data dependent now.
Okay.
Since you don't, if you know Q, then, so we'll see, like if you know Q, that's the best you can do. If you know Q, this projection you can compute and that likelihood ratio will still be a martingale, but otherwise may not, more generally it may not. Thanks. Any other questions? Okay. So let's consider an example. Thanks. So we will see that likelihood ratio test now. So suppose you are in the setting where so your script P is a collection of distributions with support in 0, 1 and mean is with mean equal to m. So this is a set. And let's say Q is again a distribution with support in 0, 1 with mean strictly less than n. So it's outside P, but it's still supported on 0, 1. So KLinf, which we introduced in the previous slide, that is the scale projection function. This is just the definition of that. Now this is an optimization in space of probability measures. You can talk about its dual formulation, right? This is a minimization in space of probability measures. So the dual would be a maximization problem. If you do the computations, you can show that this is equal to expectation under Q of log of some 1 plus lambda scale terms, okay? Take this for now. This requires a proof, but it can be shown. In particular, so this set is precisely the set where this is positive, otherwise this log will blow up. So this set is precisely the set where this is positive. Suppose this is achieved, so you can say that there is a lambda q that maximizes in this. So this quantity is exactly expectation under q of log of certain things. You would expect a log here because scale divergence has a log there. Yeah. We will try to make use of this term here. Now observe that for every fixed lambda, the random variable, so 1 plus lambda times x minus m, this is non-negative by constraint here. This set here was precisely the set where these are non-negative. So if you consider any feasible lambda over there, then this argument of log is non-negative. Moreover, if you consider, so all the elements in P were mean m random distributions. So if you take the expected value of this under P, this is exactly 1. Yeah? So this is mean 1 under everything in P. So we have a collection of random variables which are mean 1 and are non-negative. Product of these would give you a martingale. So one way to construct a martingale is to take product of mean 1 non-negative mean 1 random variables. So yeah, so we get a non-negative super martingale, or we in fact get a martingale in this case, which is just product of 1 plus lambda q. So for every fixed lambda here, we got a martingale. In particular, we'll put this lambda q here. We'll pick this lambda q, and we get a non-negative martingale. And now, once you have a process which is actually a non-negative martingale under everything in the null, you can define a stopping time with respect to that. We saw that ensures alpha correctness from Wheel's inequality. So, by the way, to answer your question, this is precisely the likelihood ratio between Q and this element here. So, this element here is, so the density of it at x is Q of x divided by this. Okay. Yeah, and it's now very easy to see that this process also satisfies the growth condition because that's how we designed it. So 1 by n times log of this process, this is nothing but 1 by, so it's the empirical average of log of these terms here. Now xi's are IID, so by law of large numbers these converge to KLM. That's why we picked this. If you picked anything else here instead of lambda q, it would not converge to this, it won't.
So
Yeah.
how do we know lambda q?
Yeah, here we know q, right? So we are assuming that
We know q.
so q, since q is point, so we know the exact q.
Sure.
If we are in composite setting, we will no longer be able to do this.
So, but even if, irrespective of what my script p is, lambda q is the
Right. Right.
Okay.
So the script p is captured in this formulation. If you change p, this formulation will change here. It will no longer be this.
For that, we don't need to know many samples or anything.
There is no sample here. This is just,
But
yeah.
x over there is.
So this is just this expression, and everything here is known for now. Since we are in point alternative setting, we know everything over here. So there are no samples here. But from here we got an idea of what the process should look like because we want to match this growth condition. This is the term that appears captures the complexity. So from here we get an idea of what the process, at least what are we targeting for. That's this quantity. And this suggested us the martingales here. There are martingale terms sitting here. So now once we have data, you can construct martingales using the bits and pieces over there. Yeah. Okay. So to answer Anand's question as well, earlier question about heavy tail, that's where this will change. You would similarly get 1 plus summation of lambda I x minus m, depending on how you describe your heavy tail class.
Okay, so here you at least assume that your expectation exists.
Yeah, I'm in fact assuming much more. Here I'm assuming that they are supported in 0, 1. They are bounded random variables right now.
But that cannot be hermetic.
No, if you relax that boundedness assumption and let's say you describe your class with second moment bounded by a constant.
Second moment bounded by constant, that's not also like very heavy.
Yes, but 1 plus epsilon bounded by a constant for any epsilon.
Then how will it be?
So instead of x, you would have mod x to the power 1 plus epsilon minus its bound there. So whatever constraints you have, you will get summation of lambda and you get martingales over there. Okay, so I think in the interest of time, so okay, one can show, so now that we have these two conditions that we identified from Wald's setup, one can show that such an upper bound also, one can prove such an upper bound. Okay. So now let's go to composite versus composite. I'll not go into the proof sketch, it's not even in the slides. But yeah, so in composite versus composite, we cannot use this test, but let's try to get a picture of how to do that. So right now we saw a composite null and point alternative, and then we saw this scale projection captures the complexity in terms of 1 by alpha, dependence on 1 by alpha. So we saw a lower bound of the expected number of samples of log 1 by alpha divided by the scale projection term. And this is the dominant term in alpha. Now, once you have composite setting, there is also a charge. So, in the previous setting, you knew what Q was. And then this was the dominant term in the dependence on KLinf as well. But once you do not know Q, so this is still a lower bound because this is a lower bound for a simpler setting. So, this is still a lower bound. Yeah, but once you do not know Q, there is another lower bound. I see. Okay, I think I'll come to that lower bound later. But so let's first look at a test. Even in the composite setting, this is a lower bound because this was a lower bound for a simpler setting. So this is a lower bound. Let's try to modify the test from the previous slide to achieve this lower bound even in the composite setting. Yeah. So let's go back to the previous setup. Earlier we had this set. And there was a point earlier. Now let's make that as well set, which is collection of all distributions in 0, 1 with mean strictly less than 1. Okay. Now we did this computation in the previous slide, or we at least stated that this is equality. We can write this for empirical distribution. So Q hat n is the histogram of n samples from Q, or it's the empirical distribution. So when this is an empirical distribution, this expectation under empirical distribution reduces to empirical averages. Yeah. Now recall these are the conditions for matching the lower bound. You want to construct a martingale and you want to satisfy this growth condition. We can think of this with equality here. And yeah, so we also saw earlier in the previous example that for every fixed lambda, this process is a non-negative martingale or super martingale under everything in the null. But previously we were able to use a particular lambda q, which was corresponding to the fixed q. Now we are no longer able to do that. But since this process, so now we don't know which distribution is generating the data, we want to learn that. We need to learn that. So notice that since for each fixed lambda this is a martingale, mixture of those with respect to any distribution is also a martingale. Yeah? So you pick any distribution on lambda space, which is this set dots here. You pick any distribution on that. The mixture of these processes is also a martingale. Okay? Now, right. So now we have a free parameter here, or we have some degree of freedom, which is how do we choose this distribution. So we want to choose f such that some condition is satisfied. What is this? So we wanted to, so just stare at this bound here. So we want to choose a mixture such that this inequality is, or this equality is satisfied. So this is just rewriting that. If you divide that by m, this term cancels, and this is just rewriting that blue equation of inequality on in the bottom. So we want to choose a mixture such that this condition is satisfied. Yes? Now, this is nothing but a regret bound. So n KLinf, this is maximum wealth in hindsight. You can think of this as for the wealth or gain of the maximum in hindsight strategy. And this is your mixture strategy. Yeah? And we are asking for a mixture strategy such that it has a sublinear regret. Okay? So yeah, so this is, so we will choose this. If you can pick a mixture such that this is sublinear, we can do that. In fact, a uniform mixture works. You can show that a uniform mixture has log n or some constant times log n degree. So if you pick your process to be this quantity, or this n times empirical k length adjusted with the log n or constant times log n degree bound, that satisfies this condition. Yeah. So any mixture works. In particular, uniform mixture also works. Yeah, and if you use this En with the degree bound for the uniform mixture strategy, which is I think half log n or 1 log n. So if you use that in your stopping rule, then you match the lower bound. You get this condition. Yeah.
So yeah, I just I'm a bit lost. So Q can be anything from this like
Yes.
calligraphic Q.
Yes. So since you don't know Q,
So any structure that we know about to know.
no, so we know that they are from bounded support and mean less than n.
That's it. Okay. And then
Yeah. So you want to now learn which distribution is generating the data. So in the last example we saw, if you know that, then you can use the corresponding lambda q martingale here. So now, in order to learn, let's take a mixture of, so we don't know, let's put a prior on all the lambda space. We don't know which particular lambda.
What can be what's the range of lambda?
Yeah, so it's in a bounded range. So the condition here is that these are positive. Since xi's are in a bounded range, lambda can be shown to be an interval.
Okay, so
You can put a
basically
uniform.
Start with prior uniform bound. And
You can start with uniform.
And then you try to get minimize some quantity to get the optimal lambda as a
Yeah, you don't really need to do that. So once you observe that this is a wealth of your mixture strategy and this is the best wealth in hindsight, this is just a regret bound condition that you're asking for, and any sublinear regret bound is sufficient to match to satisfy the growth condition. So of course, the better your mixture strategy is, the smaller this thing will be and the faster you will get. So the small of terms, O terms will show up in small or log 1 by alpha terms. So in this case, even uniform works. Okay? Yeah, but of course that's not a good thing.
Empirical Q we are only taking just for comparing.
So the strategy, so the test that you, so sometimes like implementing these mixture martingales may be hard. So instead you can also implement this to design your test. You can use this as your process. So once this process exceeds the threshold, that's when you stop. Now notice this is a convex optimization problem in one dimension. So this is implementable.
Can do better than this uniformness or does
You can do better. In fact, this will not match the other lower bound. You need to do better.
So you will optimize.
No, in the implementation, I don't want to optimize, but you can do those calculations offline. It turns out you can have a log and regret here.
So
And
you will find a particular lambda that is or no.
no, so you will find a particular distribution and get a handle on that regret of that particular mixture strategy, and just implement this, because maybe this is not implementable. Yeah, so just implement this n times k length, which is a convex 1D convex optimization. Adjust it with the regret bound. That's your process, and once that process exceeds the threshold, you stop. Okay. Okay. So yeah. So this is what we saw for the point composite versus composite dependence on alpha. But so this dependence on alpha is tight, but the dependence on k length here, or the separation of the data generating Q from P, that's not tight. Okay. So we saw that this lower bound was for the was tight in the case when Q was known, in particular when this set was actually a point. That was tight. But now there is an added complexity of searching where the true data generating distribution is. So our lower bound should capture that as well. So what we show is, in fact, a lower bound of this form shows up. So forget about this lim sup here. Expected number of samples is at least, let's forget. So f delta is 1 by separation square, log 1 by separation square. So the dependence on k length is actually 1 by k length, log 1 by k length. And so yeah. So this lower bound basically captures the dependence on the separation of unknown data generating distribution from the null set P. And yeah, this is the dominant term in 1 by Kalen. I don't think I have time for going into the test that achieves this. But so this is the same setup as we saw for the previous example. And there we had a regret bound here. We said that there's a uniform mixture strategy which has half log n as regret bound, and that achieves that lower bound. Instead, if you come up with a mixture strategy that has a regret bound of some constant times log n, that achieves in fact the other lower bound as well. And yeah, such a mixture strategy was already known but was not realized until recently. It was already known in Robin's work in 1960s for Gaussian data. Yeah, and you can prove a regret bound which holds with high probability of order log n. Yeah, so just to conclude, we saw in the point versus point setup, we saw what Wald did and tried to extract what were the properties of Wald's test that made it optimal in different senses. We tried to extend those to composite versus point and composite versus composite settings. And in particular, we saw that the scale length based separation measure is what captures the complexity of the problem in both the regimes, Ferrell's and Wald's regimes. Yeah, thank you.
Yeah, let us thank Mr. Anwar. Quite strong mathematics. So any questions from the students?
Initially, what if
It's like I don't understand that much math because I'm not blessed with maths. But initially, what if the distribution comes from the P only, not from Q?
Right. So you want to ensure, in that case, you want to ensure that you don't stop.